Aloha students, we're going to move on with section 1.2 and talk about classifying and storing data. In this section we'll also talk about the important topic of populations and samples. So let's move on here, and the first slide shows the idea of a population and a sample. So a population, some bigger group usually that we are interested in, and often it's almost impossible to get all of the data for the population. So we resort to studying the population by taking a sample of that population. Now, we in subsequent chapters will talk a bit more about appropriate sampling techniques and so on. But the most important thing you should know is that the sample that you get needs to be representative of the population. There's a number of ways that can happen, but the key way is usually that they're randomly selected. We don't just go out and willy-nilly pick, but we might use some biased judgment in doing that. Imagine you were asked to interview some people that were walking by on the street or here at the university, and one person walks by with a smile on their face. You'll be happy to talk to them, right? The next person walks by and they're looking kind of grumpy. You'd be much less likely to talk to them, and that would represent some kind of a bias if we only talk to the smiling people and so on. So the idea is to get representative data, but it's very seldom that we get the entire population. Sometimes that could happen if we've got, like if I was studying students in a university and I've got records of all the students, I could possibly look at the entire population. But many times we'll be doing our statistics by sampling. So the definition of a population is the group of interest for our study. Whatever it is that we're studying, the population is the group of interest. If I were, let's say I went to a river, and I want to study if there's any contamination in that river, then the water in that river would be my population or group of interest. Out of that water, I'm going to take some samples and try to get estimates of any contamination that might be in the river. So the sample is the portion of the population for which we will or have collected data. And that distinction is very important, and we have to look. Sometimes you'll be handed a set of data and you'll be told you have a sample here, but you should always say, well, what's the population that this sample is representing? Because that bigger group might turn out to be what you're really interested in, but the question is, can we say something about the population based on our sample? And we often do that, and we'll talk as we go forward more and more about the ways to do that. So populations are defined by things like location, time. It could be all of the students that have been here since 2015. For example, or characteristics. So here's an example, all golfers at Turtle Bay in 2018. That's the population of interest if I was studying something about the experience that those golfers had. So the collection of all data values that would ever occur for a group are the population. And you can see where sometimes that would be very difficult to get all the data. So my favorite example of this is, suppose I was a manufacturer of dynamite. Obviously, if I want to know whether or not dynamite works, I have to set it off, right, and explode it. If I tried to sample the entire population, I would have no dynamite left to sell, right? It makes no sense at all to look at the whole population. So we would take a judiciously selected sample from that population and test whether or not they were doing what they were supposed to. And from that, we would make an inference about the rest of the dynamite that we didn't explode, that it's going to work well. So the samples are the ones that we actually get, and they'll be a subset of the entire population. But a good subset of the population that's representative will do a good job of representing the entire population. I'll have some illustrations of that later on, but this maybe goes beyond the point right now, other than for me to give you the assurance that a well-selected population indeed can be very representative. I should have said a well-selected sample can be very representative of a population of interest. Now, I'm going to show you where this could go wrong if we don't recognize what's happening, and it's a story from World War II. The United States military was looking, they're sending these bomber planes on runs, and this happened both in Japan and over Europe in Germany. And some of them were getting shot down, and others were returning successfully. But they were wondering about the bullet holes in the planes that the returning planes, and they collected data on those returning planes to ask the question, well, where are the shots being? Where are they occurring? You know, what's the most heavily shot up section of the plane? And so they counted the number of bullet holes in these surviving planes, and the summary is shown here on this next slide. So they normalized it. This is a good thing that anyone would do if they're collecting data. So they said that on the engine portion of the plane, they were experiencing 1.1 bullet holes per square foot of surface area. On the fuselage of the main body of the plane, 1.73 bullet holes per square foot. The fuel system, 1.55 on average. And then the rest of the plane, which would normally include the tail section, they had about 1.8 bullet holes per square foot of exposure. Okay, so that's the situation. The military looked at this data after collecting it, and you have to give them a lot of credit for collecting it, and they just had some recommendations. What would your recommendation be? If you can place armor on the plane, what sections of the plane where you would place armor? If you put too much armor on, the plane can't fly effectively and efficiently. But if you don't put enough armor on, then you don't have protection, and many of your planes are going to get shot down, which is obviously a bad thing. So this data was taken to a statistical research group that they had at the time to help interpret what was going on here. And it was led by a man named Abraham Wald. Wald is a very famous mathematician, statistician, who's very well known today because he invented some very interesting statistical procedures. But Wald looked at this data, and he came to this conclusion that the added protections needed to be on the engines. Like, that's not exactly, I mean, they're saying that those sections weren't near as shot up, so why would we put the protection on the engines? And how did he get to a conclusion like that? Well, the explanation here, once you hear it, is actually pretty simple. When most people are presented with data like this, they say, oh, I'd make sure that these sections with the higher bullet holes, with the greater number of bullet holes, should be protected. But what Wald said was, you have data that isn't representative of the entire population. The data that you have represents the planes that survived, right? The ones that didn't survive, that didn't come back, it appears that those are the ones with more bullet holes in the engines, because the ones that came back, they did not have bullet holes in the engine. So that's a pretty good sign that the returning ones didn't get shot up in the engine. But there's no reason to think over the long run that the bullet holes wouldn't be equally prevalent throughout these, but obviously those that got shot down had bullet holes in the engine. So that's how we got to that conclusion. And what he was basically saying is, we did not have data that was representative of the whole sample. Our population of interest is the entire set of planes that were sent into war, but the population, the data that we had, only represented those that returned. So we always need to be aware of what population the sample data represents. If you're looking at this PowerPoint presentation, there's a link here at the bottom of this slide that you can click on that tells the whole story there, and you can learn a little bit more. So it's disastrous to have data that doesn't represent the population of interest. And Wald figured all of that out very intuitively and brilliantly, to tell you the truth. It's a great story. So let's look at some data sources. Suppose you want to know the predominant hair color in your country. Okay, you survey a random sample of a large sample, in this case 2,500 people in your country, asking them about their hair color. Or you might, if you see them in person, you could just observe and write it down, right? So what's the population of this study? Well, it's the bigger group. It's your country. It's the people in your country, right? And it's always good to think in terms of the units that we're talking about. A person is a unit here, right? And not that we always think of people that way, but in this particular case, that's what we're talking about. The unit is a person. And the sample are those 2,500 people that we hopefully randomly selected, and we collected data on their hair color. Now, if I was going to go to this much trouble, I'd probably collect a lot more than hair color. But let's say this study was focused on hair color, and so that would be the data they would collect on each of the samples. Okay, so that's how a study is typically set up. Now, here's a study that's a little bit of a unusual, but let's talk about it. So, a national survey was published that revealed that about 2% of all American adults, which is about 6 million people, have been abducted by UFOs. Now, that sounds like a pretty strange conclusion. That's a lot of abductions. So what's the population here? I assume it's all Americans, right? All American adults, to be specific. And the sample, well, whatever people that they surveyed, right? We don't know. It doesn't say how big of a survey was. It does say it was national, so it was very broadly done. But on the next slide here, it says, well, there might have been some problems with their conclusions about the 2%. It says what they did, they tried to measure this not by asking them if they've been abducted. They said they identified 5 indicators or symptoms that often figured in the accounts of people who say they've been abducted, and then asked whether they had experienced these symptoms. For example, waking up paralyzed with a sense of a strange person or presence or something else in the room. Now, probably people may have had that happen that have really never been abducted by aliens. So they jumped to the conclusion that if you had 4 of these, then you have been abducted by aliens. So that's where this thing becomes questionable, right? Because you really can't say that they were abducted. A good question to ask might be, have you been abducted by aliens? And what is your evidence? But that's how they didn't choose to do it that way. So sometimes the whole idea of creating a measure of what you're interested in can lead to interesting conclusions. Anyway, when we collect data, we're going to collect what we call variables. And a variable is a characteristic of interest from a population. It's a little different than the X's and Y's in algebra. But what it is something that you're collecting, and it can vary from unit to unit on which you're collecting data. So, for example, if we're looking at students at BYU Hawaii, what are characteristics that we might use to describe the people that we're sampling, if we wanted to describe them? And actually, you can see you could go look at your profile and see the kind of things that they collect. So they might collect information, obviously, on your nationality, on your maybe on your height and weight, and your ethnic background. You might collect the information. Obviously, they do collect information on your GPA, your status as a student, whether you're a freshman, sophomore, junior, or senior, and so on. There's a lot of list of things that they might collect on students, right? And each one of those we could call a variable, because obviously not every person is the same. And there's hundreds of variables that we could collect, but some of those are going to be interesting to the university, and others not so interesting. And of the variables that we might collect, you're going to see 2 typical kinds of variables. I mean, there's gradations in all of these, but for us, it's very useful to classify them as categorical and numerical data. Categorical data is usually descriptive kind of information that describes things like hair color, car type, zip code, letter grades, the license plates. They're all things that can take different values on. Gender is another one, for example. These are all examples of categorical variables. And they're often used to classify the data into groups. Like, we want to know if there's a difference between men and women and their GPAs. Well, in order to do that, you have to have a variable that says, was this a man or a woman? Go back to our gender of the hurricane, right? The name of the hurricane. That was a categorical variable. Okay? A numerical variable describes a quantity or measurement on something. So temperature, height, length, time, weight, distance. The potential numerical variables on that you could collect are infinite, but you get the idea. It's something that we're measuring or getting a quantity of. So football jersey numbers, for you that are football fans, they would normally be categorical, but it depends on what you're using them for. For example, linemen tend to be given big numbers, and running backs and quarterbacks tend to be given small numbers. Okay, Social Security numbers are just an identification. They're generally categorical, and zip codes are also categorical. They give us information about the location. So here's a little thing for us to work through. I'm going to go through these. If we were doing this in class, I would ask you to answer before we go on, but the idea is, what would the height of a bridge? Would that be a numerical or categorical variable? I'd like you to answer this in your mind before I press the button and reveal that, yeah, that's a numerical type of data. What would GPA be? Okay, your grade point average, which hopefully is high for all of you, but that would be numerical, right? One of the ways you can tell about that is it's sort of quantifying something, in this case, how well you've done in the classes. Now, the letter grade in the class, obviously an A or a B or a C, that's a categorical variable because it doesn't really represent, even though an A is better than a B, it's not really a numerical result. We'd call that categorical. Okay, the hours that you worked at a job each week, that would be numerical. It's quantifying something. Type of pet that you have, whether you prefer cats or dogs or lizards or whatever it is you might have, right? That's a categorical variable. The variety of flowers planted in a garden. Now, there could be something about the number of flowers, but if we're looking at the varieties that you plant, clearly I hope that it's clear to everyone that that is a categorical variable. The last one here, dots on the side of a die. We like to use a lot of dice experiments in statistics. And the answer to that one is it depends on what you're using it for. If you're using it, for example, you say, if I roll a 1 through a 3, I will do A, and if I roll a 4 through a 6, I will do B. You're using it to categorize things. But generally speaking, if you're using it numerically, like I'll roll 2 dice and move 12. If I roll a 10, I move 10 spots on the board in a board game. Then it's really numeric. You're adding up the die and so on. I hope that makes sense to everyone. The difference between categorical and numeric. And when we get categorical data, that's going to allow us to put the data into groups, categories, if you will. And here's an example. You're interested in the crime rate and the rank of each of the 50 U.S. states. We've got the following information. It's been given to us. We've got 4 states here and their crime rates and their rank. So that number 425 is some kind of a quantification of the crime rate in Alabama. I don't know exactly what that is, but obviously there's more crime that occurs in Alaska and California than occurs in Idaho. So the population of interest might be all the states, but we just are looking at a sample of 4 of those states right now. And we've got some variables, some numerical variables, crime rate, and the ranks are sort of a categorical variable, but the state that we're looking at, that's clearly a categorical variable. Okay, so we call the numbers in the table data, obviously, those crime rates, and we might be interested in whether the crime rate is different, what the magnitude of the crime rate, obviously, and whether they're different from one state to the next. All right, and it's clear that there are some differences here. So Idaho ranks 42nd in the crime rate. Now, this next slide and the one following it, it's just something that you'll run into sometimes when you see data. So when we get some categorical data that represents 2 groups, it's not uncommon to see it coded as 0s and 1s. So in this case, the coded data, it was gender, basically, female or male, and in this case they coded 0 as not a female and 1 as yes, a female. In modern data systems, you really don't have to do this. You could have male and female written in. Most computer programs can handle male and female rather than 0s and 1s. There is some good reason for using 0 and 1s at times, because like if I put 0s and 1s in there and I average that column, it will tell me the percent of my data that is female right off the bat. Like if that column average is 0.8, that means 80% of my data is female. But there are plenty of StatCrunch, for example, can handle the male versus female, and it'll give you all the statistics that you need. So this is not a necessary thing, but it's something sometimes you'll see in data sets that are given to you historically. And that's really all I want to do is say that. Data often come in this kind of a form where you have a column represents a variable, and then each row represents some unit that we are sampling. So like in this particular case, I think this data is birth weights. And you've got the weight in the first column, and then whether it was a male or female in the second. Again, M and F would do fine here, but in this case. And then the third column is whether or not the mother was a smoker. Now, I know this isn't a complete set of data, but it's pretty obvious that that one that was a smoker and that was a boy didn't have much. It was a very tiny baby and so on. So, but I'm sure there'd be more data, and they wouldn't look exactly like this, but you get the idea. And there could be more variables besides weight, female, and whether or not the mother smoked. But this is what's called stacked data, meaning that every row is a unit of interest, in this case a baby, and every column represents a different variable that we have measured on that birth in this case. Occasionally you'll see data as unstacked, and that's where you basically categories the data, like this case men and women, and they put all the this is heights, and they put all the men in one column and the women in a separate column, and I could look at each column separately and do an analysis of the data. The hurricane data that we were looking at earlier could have been put this way. You could have had all the male death rates in one column and all the female ones in another, but when it came to me, it was stacked data, which is the way I usually like to see it. So the unstacked versus stacked, you might see both kinds of data throughout the semester, but in any event, that is some of the ways in which you'll see data. And we'll continue this discussion in section 1.3. So thank you.